Today on Macaulay Math, we do the polynomial shuffle. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150 Pre-Calculus, Lesson 5 on polynomial functions and end behavior. Our goals for today. We're going to use transformations to sketch the graphs of polynomial functions. We're going to use the leading coefficient test to determine the end behavior of the graphs of polynomial functions. We're going to find and use the zeros of polynomial functions to sketch their graphs. And then we're going to use the intermediate value theorem to help locate the zeros of polynomial functions. In this lesson, a continued discussion of transformations will be used as a starting point to introduce the graphs of polynomials. The leading coefficient test will be used to visualize how polynomials behave as the independent variable becomes an extremely large positive or negative number. That being said, the leading coefficient test says little about the interior points of a polynomial. Thus, an exploration of the zeros of a polynomial can help to shed light on the visualization of a polynomial function. But first, let's have a formal definition of a polynomial function. Let's get started. All right, so let's start with a definition. Now, polynomial functions have the form f of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1. These three dots mean that there are an unknown number of terms in between this term a sub n minus 1 x to the n minus 1 and a sub 2 x squared. And we've been talking about polynomials so far. If we talk about a linear function, then we're talking about the last two terms. This a sub 1 is your slope, and this a sub 0 is your constant. If we're talking a quadratic from the last section, then we're talking about the last three terms, where this is your ax squared plus bx plus c. Now, n has to be a whole number, meaning that it has to be a positive counting number. So 1, 2, 3, 4, 5, 6, 7. You can also include 0. The highest power of any term of that polynomial determines the degree of the polynomial. So in the case of a quadratic, the degree was 2. The case of a linear, the degree was 1. And so it goes on from there. All terms have the form a sub n x to the n, where a sub n is the coefficient and a sub 0 is the constant term. Now, the graphs of polynomial functions have some characteristics. They are continuous, meaning that there are no gaps in between. They are a smooth curve, or a line also is acceptable. There are no holes, there are no gaps, and there are no sharp turns. Now, those are some terms that are not well defined, but if you take a look at what those things look like, as a for instance, if you have a space, a hole, and as we get into calculus, you'll see holes happen more often. This is not going to be a polynomial. If you have a gap in your graph, then that's probably not a polynomial. Now, part of it may be, but the whole thing is not. If you have a sharp turn in your graph, you're probably not looking at a polynomial function. The leading coefficient test, if you had my class physically, you probably would have seen the polynomial shuffle in Algebra 2, but it is the end behavior test. And basically what it does is it allows you to use the degree and the leading coefficient to determine what the graph does at extreme values of x and y. So let's look at this first graph that I have right here. And what we're really looking at is the blue section. We can't really use the leading coefficient test to determine what happens around the origin. We can only use it to determine what happens as x goes to negative infinity and x goes to positive infinity. Now, this is an example of an end behavior for if the degree is even, 2, 4, 6, or 8, and the leading coefficient is positive. And so what happens is that if the degree is even and the leading coefficient is positive, it's going to go up to the left and it's going to go up to the right. And we'll talk about how to write that here in a later example. Now, if the degree is even and the leading coefficient is negative, then the end behavior, and again, the blue portion says that as I go to the left, the function goes down, and as I go to the right, the function goes down. The next option that we have is if the degree is odd, so 1, 3, 5, 7, and the leading coefficient is positive, then as x goes to the left, the function goes down, and as x goes to the right, the function goes up. Finally, if the degree is odd and the leading coefficient is negative, then as x goes to the left, the function goes up, and as x goes to the right, the function goes down. Terminology for zeros of a function: if f is a polynomial function and a is a real number, then the following statements are all equivalent. And so if one of these are true, all of them are true. If a equal to x is a zero or a root of a function, then a equals x is a solution to the polynomial function f of x is equal to 0. X minus a is a factor of the polynomial, and a0 is an x-intercept of the graph of f. And we will use that to find some polynomials and examples later, and I'll refer back to that when we get there. Finally, as far as new information goes, we're talking here about multiplicity. For a polynomial function, if you have a factor x minus a to the k power, these are what we're going to call repeated zeros or repeated factors, then the 0 x equals to a has a multiplicity of k. And so when we talk about what the graph looks like with different multiplicities, if k is an odd number, then the graph crosses the x-axis at whatever a is. And if k is an even number, or you have an even multiplicity, then the graph just touches the x-axis but does not cross the x-axis at a. So for my first example here, it says use transformations to describe the function, and we have g of x is equal to x minus 2 quantity to the third power minus 3. In terms of the parent function, f of x is equal to x to the third. So I see two basic differences from this first g function to the second f function. And the first one is this minus 2, and the second one is minus 3. And as we do all transformations in previous lessons, what we'll do is we'll pick a random number, plug in, and then we will list the functions as they happen. So the first thing I'm going to do is I'm going to pick a random number to plug in for x, let's say 5. When I plug in 5, the first thing I do is subtract 2. So I'm subtracting from the variable. I haven't done the function yet. That will be a translation. 2 units right. And remember, when it's on the inside, when you're doing it to the variable, it's opposite of what your intuition might say. Then after I've subtracted the 2, I will take that result to the third power, and as we can see here, that is the function. After I've cubed, then I will subtract 3, and so that is going to be another translation. 3 units down. And so what we can do to check that is we can go to Desmos, type in f of x equal to x raised to the third, and then we'll say g of x is equal to parenthesis x minus 2 close parenthesis raised to the third, and then minus 3. And just so real quick, the 0.00 we can see has been translated 2 units right and 3 units down. So I feel fairly confident that I have done that correctly. Next, it asks, do the following functions have the same end behavior? Why or why not? Well, we can check that really quickly through Desmos, and then we can refer back to the leading coefficient test to determine why we get our answer. So back to Desmos. I have the first function graphed here in green, and we can see that as x goes to the left, the function goes up, and as x goes to the right, the function goes down. Now, if I click on this second graph, we see, again, as x goes to the left, the function goes up, and as x goes to the right, the function goes down. So even though there's a lot of other stuff going on, the end behavior seems to be the same. And so I refer back to what we talked about in a previous slide. And so this is an instance where we had an odd degree polynomial, and we can see that the highest power of any term is going to be x to the third. So even though there's this extra stuff, the degree of both f and g is 3 in both instances. In fact, the leading coefficient, because to get rid of these parentheses, I would have to distribute the negative 1/3 to each term. And so the leading term for both f and g would be the same. And so since the leading term is the same, and it doesn't even have to be the same, we need to have the same degree and a same sign, positive or negative, for the end behaviors to be the same. So when I look at this thing, again, when I say that in these red dotted areas that I can't say what's going on near the origin, all I can say about it is what's going as we get to extreme values along the x-axis, both left and right. That's what I mean here. I can't say a whole lot about what's going on in the middle. I can only say something about what's to the left and what's to the right. So my final answer for this one will be, so we can say since the degree of f and g are the same, and the leading coefficients have the same sign, the end behavior is the same. All right. Use the leading coefficient test to describe the left and right hand behavior of the polynomial functions. So here's what we're going to do. We're going to have a general setup for all of these questions in the practice work. And what we'll do is we will say as x goes to positive infinity, f of x goes to blank, and we're going to have to fill in that blank. And as x goes to negative infinity, f of x goes to blank. And we have to fill both of those in. Now, what I want to do first is I want to use the notes to actually answer this thing, and then I'm going to put it in decimals to check to make sure we were correct. So if I'm looking at this thing, this 4 divides into all 3 of those terms. Now, I'm not going to do it all because I don't care about the whole thing. I only care about the leading coefficient and the degree. So I only care really about this portion of the function right now. And so I am going to say that yes, it is 3/4 x to the 7th, and then it would be minus. Now, I would have to divide the 4 into all of these terms if I was simplifying. But again, we don't care about that because all we need is the degree and the leading coefficient. So in this case, my degree is odd and my leading coefficient is positive. All right, so if I go back up to the notes, these are both degree even, so we're not using those. And so here is a degree odd and the leading coefficient is positive. So as x goes to the left, the function goes down, and as x goes to the right, the function goes up. Well, let's look at what we wrote in our generalization. So we're always going to start with this. So as x goes to the right, that's what that means, towards positive infinity, we know that the function is going to go up. So it's going to go to positive infinity. And as x goes to negative infinity, the function is going to go down, so it goes to negative infinity. Now, let's check that in decimals. So here I have the function entered as it was written, and again, as x goes to positive infinity, the function goes to positive infinity, and as x goes to negative infinity, the function goes to negative infinity. All right, use the given function to find all of the zeros algebraically, then use a calculator to verify the zeros. Now, remember we said earlier that a zero has many equivalent definitions and statements. And so if it is a 0, then the one that I'm looking at, it is an x-intercept of the graph of f. So what we're going to do is we're going to try and factor. And so the first thing, I'm going to factor out t. So I'll have g of t is equal to t times t to the fourth minus 6t squared plus 9. And here I'm going to try and factor the quadratic form. And so I need two factors of 9 that add up to -6. Well, I can do that. So I have t, and then I'll have t squared minus 3, and then t squared minus 3. So all of those. If I want to find the zeros algebraically, one way is I'm going to set t squared minus 3 equal to 0 and solve. So I've got t squared minus 3 equals to 0. If I add 3 to both sides, I'll get t squared equals 3. And then I'll take the square root of both sides, and I'll have t equals plus or minus the square root of 3. And so those are my two zeros. And so since these two factors here are the same, my zeros will be plus or minus the square root of 3. And then this factor t right there, that'll also give me a 0 of 0. Now, because I have two of these things, I should end up with the graph touching the x-axis. In this case, it's the t-axis, at positive and negative square root of 3. So before we even get started, what is the square root of 3? 1.732 is the square root of 3. And so what I'll do is I'll type in that equation. And we can say a few things about this. Remember, the leading coefficient is positive, the degree is odd. So again, the end behavior as x goes to positive infinity, the function goes to positive infinity, and as x goes to negative infinity, the function goes to negative infinity. But we can see right there, those numbers match up, and since they were double zeros or had a multiplicity of 2, it didn't go through the x-axis, it touched the x-axis because they were double zeros. And since t only appeared one time, the graph passes through at 0. All right, let's do another. It says find all of the zeros and determine the multiplicity of each 0. So again, we're going to factor. And in this case, I'm looking for the greatest common factor, and the biggest thing that I can divide out of all of these three terms is x squared. And if I divide x squared out, x to the fourth divided by x squared is x squared. X to the third divided by x squared is just x. And then 20x squared divided by x squared is just negative 20. And here I'm going to factor. I'm going to factor the quadratic. And so I need, and if you can't factor it, that's okay. You can always use quadratic formula. But I need two factors of negative 20 that add up to negative 1. That's pretty easy. x minus 5, and then x plus 4. Negative 5 times 4 is negative 20, and then negative 5 plus 4 is negative 1. All right, so my zeros. Let's make a list here. And what makes x squared 0? Well, 0 makes x squared 0. What makes x minus 5 0? Well, 5 makes x minus 5 0. And what makes x plus 4 0? Well, negative 4 makes x plus 4 0. And so if I look at this, this one has a multiplicity of 2. This one, because there are two x's, this one has a multiplicity of 1 because there's only one factor, x minus 5, and this one has a multiplicity of 1 because there's only one x plus 4 factor. And so when I look at this thing, before I even graph it, I know quite a bit. I know that this is a fourth degree polynomial with a positive leading coefficient. It has zeros at 0, 5, and negative 4. It's going to pass through the x-axis at 5. It's going to pass through the x-axis at negative 4. And it's just going to touch the x-axis at 0. So let's go to Desmos and check to make sure I'm right. And even though we can't see everything, let's open it up so we can see everything and review our method here. I don't have to do a whole lot with the x's. I see the 1, 0. I'm just going to make this one right here. I'm going to make it, let's say 8, and then I can see it. Now, I can't see the bottoms, so let's use that powers of 10 method. So to do this, we're going to change the y's. And we still want our negative out there, but we'll start with 1, and then we'll start adding zeros. So there's 10, there's 100. It doesn't look to me like I want to need 1,000, because if I do, see it gets real small. So let's just make this 500, negative 500. And even that's a little big. But here we can see clearly it crosses the x-axis at negative 4, 0. It touches the x-axis at 0, 0. And it crosses the x-axis at 5, 0. Find a polynomial with zeros, 0, 1, and 6. And so essentially we're doing the opposite of what we did here. We factored to find the zeros. And so what we're going to do is we're going to make factors and then just multiply. So my polynomial expression. So what I'm going to do first is I'm going to make factors. So if you have the 0 as one of your zeros, this is one that's so easy that it often confuses students. And in general, it's just going to be x minus whatever number is there. Well, x minus 0 is just x. The next one will be x minus 1. And then the one after that will be x minus 6. And all we're going to do is multiply. Now, I want to make it easy on myself. And so distributing an x is the easiest thing to do. So I'm going to multiply the last two factors. And we're going to distribute. So I'm just going to bring this x down. X times x is x squared. X times negative 6 is negative 6x. X times negative 1 is another negative x plus the previous negative 6x will give me negative 7x. And then negative 1 times negative 6 will give me a positive 6. And then I'm going to distribute and so x times x squared is x to the third. X times negative 7x is negative 7x squared. And then x times 6 will be just 6x. Last example. Find a polynomial with the given zeros and multiplicities. And so the first 0 is 3, and it has a multiplicity of 1. So again, I'm going to make factors. And so the factor, if my 0 is 3 and the multiplicity is 1, then its factor would be x minus 3. And if I have a 0 of 2, then its factor will be x minus 2, but it has a multiplicity of 3. So we need 3 of those factors. It is 3 repeated factors gives you that multiplicity. So I've got x minus 2. I've got another x minus 2. And to try and keep my amount of work at a minimum, what I'm going to do is I'm going to multiply factors 1 and 2, and then 3 and 4. So I'm going to multiply these two together, multiply those together. All right. So x times x is x squared. X times negative 2 is negative 2x. Negative 3 times x is negative 3x. Plus the negative 2x is negative 5x. And then negative 3 times negative 2 is positive 6. I have multiplied the first two factors. Multiplying the second two factors, x times x is x squared. X times negative 2 is negative 2x. Negative 2 times x is another negative 2x, giving me negative 4x. And then negative 2 times negative 2 is positive 4. And here we're just going to distribute. All right, I know we haven't done this yet in this particular class, but I'm going to methodically take every term in the first polynomial and multiply it by every term in the second polynomial and stack them together. So x squared times x squared is going to be x to the fourth. X squared times negative 4x will be negative 4x to the third. And then x squared times 4 will be positive 4x squared. So I've multiplied x squared times every term in the second polynomial. And so I'm going to move over to this second term in the first polynomial and do the same thing. So negative 5x times x squared is negative 5x to the third. Negative 5x times negative 4x will be positive 20x squared. Negative 5x times 4 is negative 20x. And then we'll do the same thing, and our last row will be multiplied by 6. So 6 times x squared is 6x squared. 6 times negative 4x is negative 24x. And then 6 times 4 is 24. And I'm just going to add my columns. That's why I stacked it this way, so that all of my like terms were in columns. So I'll have x to the fourth minus 9x to the third plus, well, let's see here, 4 and 20 is 24, plus 6 is 30x squared minus 44x, and then plus 24. And that is my final answer for the polynomial. And so that's all I got for today, folks. So the Star Wars fun fact of the day: Tupac Shakur auditioned for the part of Mace Windu in The Phantom Menace. That part eventually went to Samuel L. Jackson. And unfortunately, Tupac is no longer with us. Well, that's all I have for today, folks. Have a good one. Bye.